Welcome to the last video of this year. This is on Riemann Sums, which is not in your textbook, so I created kind of my own little packet. So in addition to this note sheet, you can find a little two-page booklet or something that basically replaces the textbook for this section. So as I said, in calculus, there's really three main concepts that you use the whole year. You use limits, you use derivatives, and you use integrals. So we've covered the basics of limits and derivatives. Now we're going to cover Riemann sums, which form the basis of the integral. So a Riemann sum is a method for approximating the area under a curve. And it's the basis for the calculus concept of the integral. All right, so let's just do it on a very simple curve, straight line, f of x equals x, from 0 to 4. So we can kind of see a graph of that right here. And if we want to find the area under this curve, here, if we want to find that area, well, we're just use 1/2 base times height, which is 1/2, well, the base is 4, and the height is 4. So I get 8. So it's nice and easy, right, for this particular graph. But what if it was curved, right? What if it looked like that? Well, then this method of using a triangle wouldn't work. So let's find a different way we can approximate this area. So to start off with, let's just oversimplify things way too far, and let's pretend this is a rectangle. So we're going to use the right endpoint. What that means is I'm going to draw a rectangle that covers, remember we're going from 0 to 4, so we're looking at that range right there. I'm going to draw a rectangle where the peak is determined by the value of the function on the right side. So I'm going to look at this rectangle right here. It happens to be a square, but we'll call it a rectangle. So when I look at that, what's the area of that? Well, it's the width is 4, the height is 4, so the area is 16. Not a great estimate, right? We know 8 is the exact answer. But now let's see, what if we use two rectangles? So now I'm going to go, instead of, again, we're going from 0 to 4, I'm going to cut it in half, go from 0 to 2. So from 0 to 2, cut that off and draw a rectangle. Again, this one happens to be a square. And then the next one, I'm going to draw a rectangle here. Now notice, what's the area of the first rectangle? Well, it's 2 times 2, so 4. What's the area of the rectangle? The second rectangle, it's 2 times 4, which is 8. So I get 12 as my answer. So let's do it with 4 rectangles. So now, since we're going from 0 to 4, they're each going to have width 1. So here's 1, here's 2, here's 3, here's 4. Now these each have width 1, so 1 by 1 is 1, 1 by 2 is 2, 1 by 3 is 3, 1 by 4 is 4, so I end up with 10. Again, our answer was 8, so we're getting better and better as we go through here and do it. So let's do one more. Let's do 8 rectangles using the right. So now, since I'm going from 0 to 4, each are going to be width of a half, right? If I divide 4 into 8 equal spots, they're each going to be a half. And I'm going to, again, draw them so that the rectangles connect with the function on the right endpoint, the right side of the rectangle. All right, so now if we look at this, let's just write out the calculation that we're going to do here. It's going to be 1/2 times 1/2. Again, because the first one is going to be 1/2 always, because that's the width, right? The width of all of these rectangles is 1/2. So plus 1/2 times 1 plus 1/2 times 3/2 plus 1/2 times 2 plus 1/2 times 5/2 plus 1/2 times 3 plus 1/2 times 7/2 plus 1/2 times 4. Hopefully you can see where I got all those values for. Again, 1/2, because each of the widths of these rectangles is 1/2. And then again, notice the height of the rectangle is the value of the function at the right endpoint. So remember, we're using y equals x. So when I look at that, so the right endpoint here on the first one is 1/2. So that's where this 1/2 comes from. And then the right endpoint on this guy here, let me switch colors so it's a little bit easier to see. The right endpoint on this guy here is equal to 1, 1.5, 2, 2.5, 3, 3.5, 4. And so that's where all those values came from. Now, one thing that might make it easier is notice I could have just, all these things have a factor of 1/2 in them, right? They all have the same width, right? 1/2, 1/2, 1/2, 1/2, etc., all the way through to the end. So I could make it a little bit easier, and I could rewrite it, and I could have just written 1/2, and then I could have done 1/2 plus 1 plus 3/2 plus 2 plus 5/2 plus 3 plus 7/2 plus 4. And we could do that every single time. So let's just go ahead and actually add those all up. So 1/2 and 7/2 is 4. 3/2 and 5/2 is 4. 1 plus 3 is 4. And yeah, so let's see here. 4 plus 4 plus 4 plus 2. So I end up with 18 times 1/2. So I get 9 as my answer. All right, so I think I might have made a mistake in something that I said. No, I don't think so. Yeah, 4, 4, 4, 4, and then 2. Yeah, so 18 divided by 2 gets me 9. All right, so now this is, you notice, as we look at this process, remember we know the answer was 8. We got 16, 12, 10, 9. Notice if I'm looking at all of these, they're approaching 8, right? So if I took, you could surmise that if I took the limit as the number of rectangles goes to infinity, that this would approach the actual area under the curve. And that's what we end up doing, and that's called the integral. But we're not gonna go that far in this class. We're just gonna always do the finite case. But you can kind of see where this is building up. So if I did this with 11 billion rectangles, we'd get pretty close to 8. And if I let it go to infinity, the limit would be exactly 8. All right, so one of the things is to kind of keep in mind is now we're going to be doing it on a different function, f of x equals x squared, but let's not overcomplicate things. It's still going to be very, very, very similar. So we're going to use 6 rectangles and using the left endpoint, right endpoint, and midpoint. Now, let's actually start off. I should have probably switched these orders. Let's start off with the right endpoint because we're kind of familiar with that. So if I look at this graph, so here at 1, here at 4, here we're at 1, here we're at 16, right? So, and again, that's just plugging into that function f of x equals x squared. Now, if I draw with the right endpoint, again, this is not going to be super accurate here, but notice what I'm going to be able to do here. Oops, I'm doing 6, not 8, but you get the idea. But basically what I'm going to be doing here is, again, notice if I have 6 rectangles and I'm going from 1 to 4, how wide are my rectangles going to be, right? So if I'm going from 1 to 4, my rectangles automatically are going to be a width of 1/2, right? So if I go from 1 to 4, I could divide that into 6 equal spots, 1, 2, 3, 4, 5. Notice each of these is going to go by 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. If I use the right endpoint, what I'm going to be doing is I'm going to be plugging in this guy, this guy, this guy, this guy, this guy, and this guy. If I plug in the left endpoint, I'm going to be plugging in this guy, this guy, this guy, this guy, this guy, and this guy. So let's just go ahead and work this out. So the width is going to be 1/2 for each of these. And again, notice I have that 1/2 that I was able to factor out in part E up here. So I can just factor out 1/2, and I'm going to just plug in, since we're using the right endpoint, we're starting at 1, I'm going to plug in f of, I'll do it in decimal this time, 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5 plus f of 4. And so that ends up being 1/2 times 1.5 squared plus 2 squared plus 2.5 squared plus 3 squared plus 3.5 squared plus 4. So let's go ahead and do this. You could use a calculator if you want. Let's see here, 1.5 squared is 2.25 plus 4 plus 6.25 plus 9 plus 12.25 plus, oh, that's 4 squared plus 16. So you get 1/2 times 4 plus 9 plus 16 is 29. And 2.25 plus 6.25 is 8.5, 20.75. So I get 1/2 times 49.75, which is equal to 24.375. All right. Now if we do the left endpoint, it's going to be very, very similar, except instead of starting in by 0.5, what I'm going to end up having is I'm going to start at 1, and I'm going to end at 3.5. So again, you can kind of look at this graph, these graphs up here. If I were to look at the left endpoint on, say, part E, or sorry, let's do part D. If I looked at the left endpoint, my first rectangle would be here, my second rectangle would be here, my third rectangle would be here, and my fourth rectangle would be here. So notice, in this case, I'd be plugging in 0, 1, 2, and 3, even though I'm going from 0 to 4, right? Just so it's going to be f of 1 plus f of 1.5 plus f of 2 plus dot, dot, dot. I'm going to plus f of 3.5, and that's the last one. Because when I do that, that's 6 rectangles. If I went all the way to 4, that would actually be 7 rectangles, which would not be correct. So it's 1 squared plus 1.5 squared plus dot, dot, dot plus 3.5 squared. Now, some of you might see a nice, quick, clever way of calculating this, because we already did it on part B. The only difference is we're missing this 4 squared is not over on part A, but there is a 1 squared. So basically, if I subtracted 16 from our answer, or from what's in here inside the parentheses there, but then I added 1, because that's what 1 squared from this guy, I could get my answer. So I'm basically going to subtract 15. So, right, subtract 16, add 1. So subtract 15 from 49.25, and I'm going to have 1/2, and then 34.75, sorry, 75, not 25, which is equal to 17.375. Again, you could just plug it all in, and I think you'd see that you get the same answer. It's up to you. Now the midpoint, we're going to do it a little bit differently. So the midpoint, again, looking at my number line, I'm going from 1 to 4, I'm going by 1/2. So here's 1.5, here's 2, here's 2.5, here's 3, here's 3.5. Right, so I'm going by that. Now if I'm doing the midpoint, well, what's halfway between 1 and 1.5? Well, I'm going to have 1.25. What's halfway between 1.5 and 2? Well, that's 1.75. Halfway between 2 and 2.5? That's 2.25, etc. Right? 2.75, 3.25, 3.75. So let's go ahead and do that. The width on all these rectangles is still 1/2 times, but now it's going to be 1.25 squared plus 1.75 squared plus 2.25 squared plus dot, 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 dot plus 3.75 squared. So let's go ahead and calculate that. Let's see here, we got 0.5 times 1.25 squared plus 1.75 squared plus 2.25 squared plus 2.75 squared plus 3.25 squared plus 3.75 squared. Now, for those of you that are industrious and that might have some programming experience, you could actually write a program to calculate all this, where you just say what the function is, um, what A is, what B is, and then and what the number of rectangles is. Hit enter, and you could program something to do this for you. But um, I'm not going to go through how to do that for sure. Um, all right, so I ended up with my answer of 20.9375. Now, one of the things that you might, so which of these is probably going to be the best estimate? Probably the midpoint. Um, let's take a look at what I'm talking about here. And before we go ahead, I just realized I made a little error, little math mistake there. That's 24.875. Right, what I had written would give me 48.75, not 49.75. So 24.875. So let's take a look at what this looks like. So here's our graph of y equals x squared. We're looking at it from 1 to 4. And so notice using the right endpoint, notice where it says relative 24.875, that's kind of what we're looking at as far as our value. So the right endpoint gives me 24.75. The left endpoint gives me 17.375, which is also what we calculated. And then the midpoint gets me 20.9375, which is, I believe, is what we calculated here, 20.9375. So now I just want to kind of show you, again, as I'm doing that, watch what happens to the bars. So the midpoint, notice on the right endpoint, look where the rectangles are determined. If I look at it, I'm not sure if you can see the little hand that I'm drawing there. Let me see if with the cursor here. The right endpoint is where it crosses the function. Now if I switch to the midpoint, now notice the midpoint was where it crosses the function. That's why we plugged in 3.75, because f of 3.75 gets me my height. So, and then finally, left endpoint, you can see it connects on the left side here. So you can see the left endpoint would be an underestimate, because look at all these little triangle looking shapes. They're not quite triangles, but because they're curved, but little triangle looking shapes that we're missing. The right endpoint is going to be an overestimate, because look at all these triangle looking shapes that we added. And the midpoint is going to be pretty good. It's not going to be exact, because it's not the same. What's over is not the same as what's under. But it's a pretty good estimate. I think it ends up being a little bit of an underestimate, but yeah, it's a pretty good estimate. So let us find the area under the curve f of x equals sine of x plus 1 plus e to the x from x equals 0 to x equals 2 pi using 4 rectangles and the left endpoint, right endpoint, midpoint. All right, so, and here's a nice little formula that tells us how to do all this stuff. We can go ahead and, so first off, notice what's the width of these rectangles. So if it's from 0 to 2 pi and we divide it into 4, it's going to be 2 pi minus 0 over 4, which gives me pi over 2. That's the width of my rectangles, which a lot of times we'll call delta x. So, sorry, that's an arrow, just to be clear. So width, and we'll call that, a lot of times we'll call that delta x. And so then we're going to start at the left endpoint. So we're going to plug in 0. That's my left endpoint. And then I'm going to go up by pi over 2 each time. So pi over 2, up another pi over 2 is pi, up another pi over 2 is 3 pi over 2. And so there we are. And then we basically just put that pi over 2 out in front, plug those in, add them up. So it doesn't matter how messy this function is. That's the reason why I'm doing it this one. So it doesn't matter how messy that function is. The process is still going to be the same. It's just sometimes we might have to use a calculator. So let's go ahead and plug it all in. So I'm going to have pi over 2. Oop, and I messed that up. Second pi over 2. We're going to take that times. And then we're going to have some of it I'm just going to plug it in rather than plugging in sine, because sine of 0 we should be able to know is 0. So sine of 0 is 0. I'll even write that in there. Plus 1 plus, and then we got e to the x, so e to the 0, which is 1. So that's f of 0. Now let's do f of pi over 2. So sine of pi over 2 is 1 plus the 1 plus e to the pi over 2. Well, I don't know what that is, so let's go ahead and second e to the pi over 2 plus sine of pi, which is 0, plus 1 plus e to the pi. Oop, I did not mean to do that. E to the pi. And then plus sine of 3 pi over 2 is negative 1. So plus negative 1 plus 1 plus e to the 3 of pi over 2. Now, assuming I didn't punch something in wrong on my cumbersome emulator, I get 226.62, let's say. Now, the easiest way to do this for when I do the right endpoint is this is going to be exactly the same, except on the right endpoint, I'm going to, I'm going to cross off 0, but I'm going to plug in 2 pi. And it's nice to recognize that pattern, because now I can just go back to what I plugged in before. And let's go ahead and go to the beginning here and delete what I got when I plugged in 0. And now let's go ahead and add what I get when I plug in 2 pi. So sine of 2 pi is still 0, sorry, 0, not 1, plus 1 plus e to the 2 pi. I get 1066. Now notice this is a huge difference. 19. Now we're not using that many rectangles, only 4 rectangles, and it's an exponential function, so that would account for why it's so bad. Now the midpoint, this one's not going to be quite as, we can't do any nice little trick for this. We got to go back to the drawing board. The width is still pi over 2, but now it's going to be f of, now it's halfway between 0 and pi over 2 is pi over 4, plus f of 3 pi over 4, plus f of 5 pi over 4, plus f of 7 pi over 4. All right, so pi over 2. Now this one, I'm just going to make sure I'm in radians. Okay, this one, we do know what, well, I guess it's about the same difficulty to plug in anything. So I'll just do it. We know what sine of pi over 4 is. That's root 2 over 2. Actually, let me just do a little shortcut here. Notice when we plug in pi over 4 into sine of x, we're going to get root 2 over 2. When we plug in 3 pi over 2, we're going to get root 2 over 2. When we plug in 5 pi over 4, we're going to get negative root 2 over 2. We plug in 7 pi over 4, we're going to get negative root 2 over 2. So basically those signs all cancel off. We get 2 positive root 2 over 2s, and we get 2 negative root 2 over 2s. So again, from here we hit, oops, I did not mean to zoom like that. So in this guy, we get root 2 over 2 plus something, plus root 2 over 2 plus something, plus negative root 2 over 2 plus something, plus negative root 2 over 2 plus something. And so notice all those cancel off. And so I'm just going to skip plugging them in at all. Just a nice little time saver. So I got 1 plus, I'm going to plug in, and then another time saver is we have 1 here, we have 1 here, we have 1 here, we have 1 here from this one right here. And so I'm going to have just 4. So I can just plug in e to the pi over 4 plus e to the 3 pi over 4. No shortcut on this. E plus e to the 5 pi over 4 plus e to the 7 pi over 4. And I would expect this answer to be not halfway between, but somewhere in the middle here of our previous two answers. So 226 and 1,000, 489, that seems reasonable. So I get 489.54. All right, so now one thing that's kind of nice is there's something called the trapezoid rule, which you can just, again, you'll deal with these more in depth. I believe it's actually Calc 2, so not AB, but probably BC. But where we just take the average of those two. So let's just go ahead and take the average of the left and the right. So this plus this divided by, oh, no, let's hit enter. Let's divide that by 2. So I just took A and B and added them together and divided by 2. I get 646.41. And then finally, there's something called Simpson's rule. You'll probably learn to explain differently, but this is the way I like to calculate it. It's a lot easier to deal with. Is 2/3 times the midpoint rule plus 1/3 times the trapezoid rule. So I get 541.83. All right, so last thing I'll kind of show you, if you're curious what the actual answer is, let's just take a look what the actual answer is. You'll learn how to do this by hand next year, but we wanted to go from 0 to 2 pi of sine of x plus 1 plus e to the x. And again, don't worry about this notation, or you don't have to know how to do this on your calculator. But the actual exact answer, I mean, I'm sure, not exact, but this is accurate to all the decimal places we're seeing. 540.7748. So notice we were off by not very much by using the Simpson's rule, which is kind of cool. We used 4 rectangles to approximate this function here, sine of x plus 1 plus e to the x. So let's take a look at that. So I used it to approximate this guy from 0 to 2 pi. So pretty cool. Anyways, that is it for this lesson. Sorry for the long video, a little bit longer than normal, but hopefully you find it helpful. And as always, I'll see you, for questions.